NEC Section 422.10 addresses branch circuit requirements for appliances, specifically stating that the branch circuit ampacity should not be less than 125% of the continuous load rating for continuously loaded appliances. Now, regarding the dryers with nameplate ratings of 79 amps, the nameplates recommend a 100 amp breaker. However, it is important to understand that this recommendation does not necessarily dictate the maximum allowable ampacity. To determine the appropriate breaker size, we need to calculate 125% of the continuous load rating. In this case, 79 amps multiplied by 1.25 equals 98.75 amps. This calculated ampacity of 98.75 amps is less than the existing 125 amp breakers. Therefore, the existing 125 amp breakers can be used without violating NEC Section 422.10. However, while the 125 amp breakers technically meet the code requirements, there are additional factors to consider. It is generally recommended to adhere to the manufacturer's recommendation of a 100 amp breaker. Using the recommended breaker size ensures that the circuit is adequately protected and that the equipment will operate safely. It is worth mentioning that the conductors and other components of the circuit must also be rated for at least 125 amps to be compatible with a 125 amp breaker. Furthermore, the application of NEC Section 422.10 is not mandatory for existing installations, but it is good practice to follow it for safety reasons. To summarize, while the 125 amp breakers are permissible based on a 125% calculation, it is advisable to consider using the manufacturer's recommended 100 amp breaker size for enhanced safety and equipment protection. When deciding on the appropriate breaker size, it's important to consider several factors to ensure both safety and code compliance. Let's delve deeper into these considerations. Firstly, understanding the nature of the load is crucial. NEC Section 210.20 and 215.3 emphasize the importance of overcurrent protection devices being loaded to only 80% of their rating when dealing with continuous loads. A continuous load is defined as a load where the maximum current is expected to continue for 3 hours or more. In this scenario, if the dryers are expected to operate continuously for extended periods, the 80% rating factor becomes relevant. To apply this rating, we need to calculate the maximum allowable continuous load for both the 100 amp and 125 amp breakers. For a 100 amp breaker, the maximum continuous load would be 100 amps multiplied by 0.8, which equals 80 amps. For a 125 amp breaker, the maximum continuous load would be 125 amps multiplied by 0.8, which equals 100 amps. Considering that the dryers have a nameplate rating of 79 amps, both the 100 amp and 125 amp breakers would technically meet the requirement of not exceeding 80% of the breaker's rating for continuous loads. However, using the 100 amp breaker would provide a tighter margin and potentially offer better protection against overloads. Secondly, the conductor ampacity is another critical factor. The conductors supplying the dryers must have an ampacity sufficient to carry the load, as specified in NEC Section 310.15. The ampacity of the conductors must be at least 125% of the continuous load, as per NEC Section 422.10. In this case, the conductors must be rated for at least 98.75 amps, which is 79 amps multiplied by 1.25. If the existing circuits are wired with conductors rated for at least 125 amps, then using the 125 amp breakers would be acceptable from a conductor ampacity perspective. However, if the conductors are rated for less than 125 amps, then using the 100 amp breakers would be necessary to comply with NEC regulations. Thirdly, the existing panel board and overcurrent protection scheme should be evaluated. The panel board must be rated to accommodate the additional load of the dryers. If the panel board is already heavily loaded, adding the dryers may exceed its capacity. Additionally, the overcurrent protection scheme must be properly coordinated to ensure that the breakers trip in a selective manner. Selective coordination means that the breaker closest to the fault should trip first, while upstream breakers remain closed. This helps to minimize disruptions and prevent unnecessary power outages. In summary, when determining the appropriate breaker size for the dryers, it's crucial to consider the following factors: the nature of the load, including whether it's continuous or non-continuous, the conductor ampacity, ensuring it meets or exceeds the minimum requirements, and the existing panel board and overcurrent protection scheme, verifying its capacity in coordination. While the 125 amp breakers may technically meet the code requirements based on the 125% calculation, it's often advisable to prioritize the manufacturer's recommendation of a 100 amp breaker for enhanced safety and equipment protection. Always consult with a qualified electrician to ensure compliance with all applicable codes and regulations. Now let's elaborate further on the practical implications of these considerations. If the dryers are indeed classified as continuous loads, which is likely in a commercial setting where they may operate for extended periods, the 80% derating factor becomes particularly significant. In this case, using the 100 amp breakers would provide a greater margin of safety and reduce the risk of nuisance tripping. Nuisance tripping occurs when a breaker trips unnecessarily due to temporary overloads or surges. By using a smaller breaker, the circuit becomes more sensitive to overloads and potential faults, providing better protection for the equipment and wiring. However, it's essential to ensure that the conductors are adequately sized for the 100 amp breakers. If the existing wiring is only rated for, say, 110 amps, then using 100 amp breakers would still be the appropriate choice, even if the panel board could accommodate a larger breaker. The weakest link in the circuit determines the overall ampacity rating. Another factor to consider is the potential for future expansion or changes in load. If there's a possibility of adding more equipment or increasing the load on the circuit in the future, it may be prudent to use the 125 amp breakers, provided that the wiring and panel board can handle the additional capacity. However, it's crucial to avoid oversizing the breakers simply to accommodate future growth. Oversizing breakers can compromise safety and increase the risk of damage to equipment and wiring. In addition to the NEC requirements, it's also important to consult any local codes or regulations that may apply. Some jurisdictions may have stricter requirements than the NEC, and it's essential to comply with all applicable codes to ensure safety and avoid potential violations. Furthermore, it's always a good idea to consult with the manufacturer of the dryers to obtain their specific recommendations for breaker size and wiring. The manufacturer's recommendations may take into account unique characteristics of the equipment or specific operating conditions. Following the manufacturer's recommendations can help to ensure optimal performance and longevity of the equipment. In summary, the decision of whether to use 100 amp or 125 amp breakers for the dryers depends on a variety of factors, including the nature of the load, the conductor ampacity, the panel board capacity, potential for future expansion, and any applicable local codes or manufacturer's recommendations. While the 125 amp breakers may technically meet the minimum NEC requirements, it's often advisable to prioritize the manufacturer's recommendation of a 100 amp breaker for enhanced safety and equipment protection. Always consult with a qualified electrician to ensure compliance with all applicable codes and regulations and to make an informed decision based on the specific circumstances. Now let's discuss how to proceed with evaluating the situation systematically. Firstly, gather all the necessary information. This includes the dryer nameplate information, the existing wiring specifications, the panel board rating, and any applicable local codes or regulations. Secondly, determine whether the dryers are classified as continuous loads. This can be done by assessing how long they typically operate at their maximum current draw. If they operate for 3 hours or more continuously, they should be considered continuous loads. Thirdly, calculate the minimum required ampacity for the branch circuit based on the continuous load rating of the dryers. This is done by multiplying the continuous load rating by 1.25 as per NEC section 422.10. Fourthly, verify that the existing wiring is adequately sized to handle the calculated ampacity. Consult NEC Table 310.15 to determine the allowable ampacity of the conductors based on their size, insulation type, and installation method. Fifthly, assess the panel board capacity to ensure that it can accommodate the additional load of the dryers. Check the panel board's main breaker rating and the available space for additional breakers. Sixthly, consult with a qualified electrician to review the situation and provide recommendations. An electrician can help to identify any potential issues or concerns and ensure that the installation complies with all applicable codes and regulations. Seventhly, if the electrician recommends using the 100 amp breakers, proceed with replacing the existing 125 amp breakers. Ensure that the new breakers are properly labeled and that all connections are tight and secure. Eighthly, if the electrician recommends using the 125 amp breakers, verify that the wiring and panel board are adequately sized to handle the additional load. If necessary, upgrade the wiring or panel board to meet the required ampacity. Ninthly, after completing the installation, test the circuit to ensure that it is functioning properly. Use a multimeter to measure the voltage and current at the dryer terminals and verify that they are within acceptable limits. Tenthly, document all work performed, including the breaker sizes, wiring specifications, and panel board rating. This documentation will be helpful for future maintenance and troubleshooting. In addition to these steps, it's also important to consider the overall safety of the electrical system. Ensure that all wiring is properly grounded and that there are no exposed conductors or damaged insulation. Install ground fault circuit interrupter protection in any areas where there is a risk of electric shock, such as near water sources. Regularly inspect the electrical system for any signs of wear or damage and promptly address any issues that are identified. By following these steps and consulting with a qualified electrician, it's possible to ensure that the dryers are properly wired and protected and that the electrical system is safe and reliable. Remember, electrical work can be dangerous, and it's always best to leave it to the professionals if you are not comfortable or qualified to perform the work yourself. Also note that specific table numbers are mentioned in this discussion of the NEC. It is important to consult the current edition of the NEC, which is updated every 3 years to ensure compliance with the latest requirements. Code requirements can change over time, and it's essential to stay up to date with the latest regulations. Let's explore the ramifications of using the 125 amp breakers when the manufacturer recommends 100 amps. Firstly, increased risk of equipment damage. The manufacturer's recommendation is based on the specific characteristics of the dryer and its components. Using a larger breaker than recommended can allow excessive current to flow through the dryer in the event of a fault or overload, potentially damaging sensitive components such as heating elements, motors, or controls. Secondly, reduce sensitivity to overloads. A 125 amp breaker will trip at a higher current level than a 100 amp breaker. This means that the circuit can sustain a larger overload before the breaker trips, potentially causing overheating of the wiring or equipment. Thirdly, potential for nuisance tripping. While it may seem counterintuitive, using a larger breaker can actually increase the likelihood of nuisance tripping. This is because the breaker is less sensitive to minor overloads or surges, which can accumulate over time and eventually cause the breaker to trip. Fourthly, violation of manufacturer's warranty. Using a breaker that is larger than the manufacturer's recommendation may void the warranty on the dryer. Manufacturers typically specify the appropriate breaker size to ensure that the equipment operates safely and reliably. Fifthly, increased risk of fire. In extreme cases, using an oversized breaker can increase the risk of fire. If the wiring or equipment is subjected to prolonged overloads, it can overheat and potentially ignite nearby combustible materials. While these are potential risks, they are not guaranteed to occur. The actual consequences of using the 125 amp breakers will depend on a variety of factors, including the severity of any overloads, the quality of the wiring and equipment, and the presence of any safety devices such as ground fault circuit interrupters. Now let's consider situations where the 125 amp breakers might be more appropriate. Firstly, high inrush current. Some dryers may have a high inrush current when they start up. Inrush current is a temporary surge of current that occurs when an electrical device is first turned on. If the inrush current is high enough, it can cause a 100 amp breaker to trip unnecessarily. In this case, a 125 amp breaker may be needed to accommodate the inrush current. Secondly, long circuit runs. If the dryer is located a long distance from the electrical panel, the voltage drop in the wiring can reduce the available voltage at the dryer. This can cause the dryer to draw more current to compensate for the voltage drop, potentially overloading the circuit. In this case, a 125 amp breaker may be needed to accommodate the increased current draw. Thirdly, future expansion. If there is a possibility of adding more equipment or increasing the load on the circuit in the future, it may be prudent to use the 125 amp breakers, provided that the wiring and panel board can handle the additional capacity. However, it's crucial to avoid oversizing the breakers simply to accommodate future growth. Oversizing breakers can compromise safety and increase the risk of damage to equipment and wiring. Therefore, the best approach is to carefully evaluate the specific circumstances and make an informed decision based on the available information. A qualified electrician can help to assess the situation and provide recommendations based on their expertise and experience. Now let's address some common misconceptions about circuit breakers. Firstly, breakers are designed to protect equipment, not people. While breakers can provide some protection against electric shock, their primary purpose is to protect the wiring and equipment from overloads and short circuits. Ground fault circuit interrupters are specifically designed to protect people from electric shock. Secondly, breakers trip instantly when there is an overload. Breakers have a time delay built into them, which allows them to withstand temporary overloads or surges without tripping. The time delay is typically longer for larger overloads and shorter for smaller overloads. Thirdly, breakers never fail. Breakers can fail over time due to wear and tear, corrosion, or other factors. It's important to periodically test breakers to ensure that they are functioning properly. Fourthly, all breakers are the same. Breakers come in different types and sizes depending on the application. It's important to use the correct type and size of breaker for each circuit. Fifthly, breakers can be reset an unlimited number of times. Repeatedly resetting a breaker after it trips can damage the breaker and increase the risk of fire. If a breaker trips frequently, it's important to identify and correct the underlying problem. Finally, only a qualified electrician can work on electrical systems. Electrical work can be dangerous, and it's always best to leave it to the professionals if you are not comfortable or qualified to perform the work yourself. Electrical safety is paramount, and it's essential to take all necessary precautions to protect yourself and others from electric shock. Some other areas we have not yet covered would include the ambient temperature of the location of the breaker. The temperature around the breaker will change its trip point. The higher the ambient temperature, the lower the trip point, and vice versa. Altitude affects the cooling of the breaker, thus can affect the trip point as well. The higher you are, the less dense the air and cooling effect is. Another factor to consider is voltage drop. NEC section 210.19a on FBN number 4 and section 215.2 ATHI FBN number 2 recommends that voltage drop on branch circuit should not exceed 3%, and voltage drop on feeder should not exceed 5%.